Now what we're going to do is we're going to figure out the electric field that exists at a point R from an infinitely long line of positive charge. With a uniform linear charge density. What is the symbol for linear charge density? Nitish? Lambda. So we have an infinitely long line of charges. Basically, it's a charged wire. As of yet, those charges are not moving, because we just have a bunch of positive charges on the wire. Okay. Our goal is to figure out the electric field that exists at a distance r from this infinitely long wire. We are going to use Gauss's law. The electric flux is equal to the closed loop integral of E dot dA, which is equal to the charge inside the Gaussian surface divided by E naught. Now, when we pick our Gaussian surface, which is what we're about to draw next, we have to pick it such that a bunch of things happen on the left-hand side. So let's walk through them. What happens on the left-hand side? Before we even pick our Gaussian surface, because we actually have to pick our Gaussian surface so that we can figure out what happens on the left-hand side, please. Emily.
It would be the closed surface integral of E dA cosine theta.
Good.
And then we'd have to figure out what our theta is now.
Okay, but what was the theta every time last time? Theta was 0. So we need the cosine of 0 degrees. Now, I did say that we might also sometimes have not the cosine of 0, but who can tell me the cosine of 90. With the cosine of 90, cosine of 90 class is 0. So we might have some where it works out to be a flux of 0 if we have a cosine of 90 degrees. Okay. So if we have a cosine of 0 degrees, we end up with a E dot dA. And what was our next step?
Yeah.
I'm sorry, I think the dot is gone. So we get then just E dA. What was our next step, Mr. P?
Plot the E.
Because
It is constant.
it's constant. And so we get the electric field with a closed surface integral of dA, and then it's E times just A. Now, the whole point here is when we pick our Gaussian surface, we need this to happen. So the shape of our Gaussian surface this time is going to be a cylinder. We're going to have a cylinder, which is our Gaussian surface. And we're going to talk about why that shape is a cylinder. So the cylinder is going to look like this. This is a Gaussian surface which is a cylinder. Now, the cylinder is going to have a length L. When we look at the side of our Gaussian surface, that's this whole side right here, we have dA at this particular point. What is please point, class, in the direction of dA. It's always outward, so dA is going to be this way. Now, we should be able to tell from the symmetry here that the electric field is going to look like this. It's always going to go outward away from our infinitely long infinitely long positively charged wire. How do we know it goes away from the wire? Meg?
I'm not sure.
Okay. I need to know why it goes away from the wire. Potter.
Because we use a positive test charge.
one other word for the pessimist.
Small.
Positive test charge. And if we took a small positive test charge, it would be repelled away from there. So we know the direction. So if you look for the side, the cosine is 0 degrees. But then we have the top and we have the bottom of our Gaussian surface. The top and the bottom. So please point in the direction of dA for the top surface. Right? dA for the top is up. So if we talk about the top, what do we get for the closed surface integral of E dA? Cosine of 90. And this is true for the top and the bottom. So the flux, or the number of field lines that pass through the top and bottom, are 0. So when we talk about the total electric flux, we really only need to talk about the side of our Gaussian surface, because both the top and the bottom have an electric flux of 0. So when we talk about this area then, this is going to be the area of the side of our Gaussian surface, or the area of the side of this cylinder. So we have charge in over E naught, charge in over E naught, charge in over E naught. Let's just bring this up here so we can talk about it. We have E times the area of the side. The charge inside the Gaussian surface. The charge inside the Gaussian surface, notice that's not the total charge of the wire. It's infinitely long, so it technically has an infinite amount of charge anyway. So we need a small portion of that. So we're going to look at it using our linear charge density. Linear charge density is equal to, what, Tim?
Coulombs. Wait.
Dimensions would be coulombs per meter, but I'm looking for the equation.
Oh. Seal graph. Q.
Charge per unit length. Right? So if we talk about in terms of just inside the Gaussian surface, this is going to be the Q in divided by the overall length of our Gaussian surface, which is L. So the Q inside our Gaussian surface is equal to the linear charge density times the length of the Gaussian surface. So we have the linear charge density times L divided by E naught. What about the left-hand side? We need the area of one side of the Gaussian surface. What is the area of this side? Tyler?
2 pi r, or 2 pi r L.
2 pi r times L. The surface area of this is going to be the circumference of the circle multiplied by the length, or the length times the width of a rectangle. That's equal to lambda times L divided by E naught. Everyone brought L to the party. It's close. We get that the electric field equals lambda divided by 2 pi E naught times r. Or if you prefer, the electric field equals 2 times 1 over 4 pi E naught times lambda over r. Therefore, the electric field equals what, Loki?
1/2, or let's say, 2k lambda over r.
2k lambda over r. So the electric field from an infinitely long wire is going to be equal to 2k lambda over r, and it's going to be directed radially outward from the wire.
Does that work if it's not?
So here's the deal. In this class, what we start with is infinitely large, or infinitely long, infinitely large objects. And the idea is we then use that to derive other things. So this is the most basic. The next thing we're going to do is actually an infinitely large sheet of positively charged particles, right? And then we're eventually going to get to the point where if we talk about a straight wire, as long as we have a straight wire and we're only talking about a short distance from that small straight wire, it's going to act like this, right? Yes, in order for this to truly work, we would need an infinitely long wire, but as long as you have, if the wire is not infinitely long, but you're only talking about short distance away from that wire, then this does work out to be true. And that's basically where we're going from here. We're starting with the most basic, which is something infinitely large, and then we derive other things from that.